Motion along a straight line. This is a very interesting yet challenging topic that most engineering students struggle with. If you're having issues completing your homework, or maybe you can't solve that exercise from class, worry not, because we are going to deep dive into the mysteries of the equations that describe the motion along a straight line. Now for this, I'm going to use a few resources available at toysandphysics.com. This first part will only cover the basics, that is position, displacement, and average velocity. Now, if you want to get more details, I recommend you to pay a visit to the site for more references. I'll be creating more videos with more details to help you advance your knowledge about this topic, right? But this first part should serve as an intro for anybody looking to learn more about the topic of motion along a straight line. Now, if you want to get a notification when these other videos are uploaded to the channel, I recommend you to subscribe and stay tuned for more content. If you like the video and find it useful, please give it a thumbs up and share it with your classmates for their reference. And well, without further ado, let's get into it. Very well, let's get started. In order to start studying the motion along a straight line of an object, say this car that I have here, which is moving from left to right, as you can see, it's moving along a straight line. That's what I intend to represent with this. In order to know its speed, its velocity, or displacement, everything that has to do with the motion along a straight line of this car, what would be a good part of a car to take into account for our calculations? And say if I, for instance, calculate everything that has to do with the movement, the motion along a straight line for this door, I can say I'm calculating for the whole car. Would be good to say that the door is representative, or can we say the tires are representative of that? Maybe the front light, the rear light. What would be that part that's good to take into account? Well, that may sound silly and that may sound like it's not important, but actually there's something that's at the bottom of the screen here that I wanted to share with you, which is a key idea that says that if all parts of an object move in the same direction and at the same rate, then we can treat the object as if it were a point-like particle. That means that we can simply say, take this car by the center and simplify everything to a point-like particle and calculate everything using that particle. And the reason why that is important is because this point-like particle, this point-like object, is going to help us simplify our study. The equations, the graphical representation, everything we do with this will help us simplify our calculations. You may not see it now because we're talking just about one car, but what if we had two cars racing and we had to represent those two cars? Well, it now gets a bit more complex, right? We have to draw two cars and kind of pay attention to every single part of the car. But if we can simplify each car to a point-like object or a particle, then things get a lot easier. And that's what we're going to do here with this car. So using that key idea, let's talk about three basic concepts, the three most basic concepts of motion along a straight line, which are position, displacement, and average velocity. That's it. If you can understand these three, then everything else will come naturally, because everything else will just be related to everything we do here. So the first one's position, and position is just a location of an object relative to a reference point. We usually take an axis like the one I have here, and it's scale, like it is this one's scale here, and in this case I think I have determined that these are meters, right? This x-axis is in meters. Now I have determined and said that this will be the origin, the point 0. This will be the origin, and everything that I locate, say -2 or 2 meters at the left side of this 0 point will be on the negative side. Everything on the right side will be on the positive side. Also, when we talk about displacement, we're going to see changes in position. Anything moving from right to left will be moving on a negative direction. Everything moving from left to right will be moving on a positive direction. And let's go to see the example here for displacement so we can learn more about that, right? What those R's here mean. So displacement, like I said before, is just a change from position, say, x1 to position x2. That change is called displacement, and we calculate it like this. Delta x equals position 2, which is x2, minus position 1, which is x1. In this case, there's another axis here that we have to represent displacement of this particle, which moves from x1 equals -2, right? It starts on -2, and then it moves to x2. Position 2 is +3. And again, we have meters here. That's important just to make sure that we know what measurement units are we using, right? So if we wanted to measure the total displacement of this particle-like object, we would simply use this equation here and replace what we have here, and it'll be like this. Displacement, delta x, displacement equals x2, right? Which is 3, +3. Then we have this minus here, minus. Then I open a parenthesis here because x1 is -2. So I want to take into account this negative sign here. And if we solve those two signs, we have a positive sign here. And this says that displacement on the x-axis equals 3 meters plus 2 meters, right? We got this positive from these two multiplying. And then delta x, or displacement, total displacement for this particle-like object equals 5 meters, right? So it's that simple to calculate the displacement of a particle-like object. Now, in this case, we can verify if our number, or if our result here is correct by simply counting the spots, the scale, right, the number of meters that the particle is moving. You won't be able to do this in every single exercise or in every single case that you have, but since this is a simplified example, we can do it here. So if we count starting from -2 until 3, up to 3 here, we can say 1, 2, 3, 4, and 5. So that matches with our number here of +5. Also remember that if this sign is positive, which we are not putting here because that's we don't display positives, we just display negatives, right? That means that the object, in this case this particle, is moving in the positive direction. That was left to right. Okay, so that's what you want to know about this displacement of this particle. That's, like I said, a very simple example, but it's just a way of explaining you this in a simple way. Now, something else you want to know about displacement is that this is a vector quantity, and that means it has magnitude, in this case 5, and it has a direction, which is the plus sign here. That plus sign here means that it's moving on a positive direction. Okay. All right, so moving along to average velocity. Let me just scroll up a little bit here. Average velocity as well as a vector quantity, and it's because we have displacement on top. Average velocity is, what if you wanted to measure not just the change in position, but also the time it takes to this particle to reach that x2 spot, that x2 position, right? So if you do that, you are talking about average velocity. When you want to measure displacement versus time, we have average velocity. Again, vector quantity, we are talking about vectors in a separate video. For now, just wanted to mention that. But average velocity is just that, comparing your displacement to the time it takes for that particle to move from x1 to x2. And in this case, I have this graphical representation here, which is the y-axis. Now we are using it for position, and the x-axis we're using it for time here, right? So as you can see, t2 x2 goes 3 3, and x1 and t1 is 0 0. So we just use this equation here, we replace everything on it, and if we solve for that, it'll go like this: x2, which is 3 meters, minus x1, which is 0 meters, divided by 3 seconds, which is t2, minus 0 seconds, which is t1. That'll give 3 divided by 3 meters divided by 3 seconds, and thus we get 1 meter per second. That means this particle-like object, it's moving at 1 meter per second according to our representation here. And that's pretty much it. Those are the 3 basic concepts you have to understand to start navigating the topic of motion along a straight line. Everything, of course, we're going to start developing more in terms of this topic, but for now, that's the basics. And if for some reason you are confused or have any questions, please let me know. I'll be more than happy to know about you. If you want to take a look at these animations and resources, you can pay a visit to www.toysandphysics.com, and you'll find more details than the ones I shared here on this video on that site. Just look for the topic motion along a straight line, and you should be fine. And there, like I said, there will be more details because I'm developing a series of videos with these concepts and problems to solve and a lot of cool and fun stuff. Okay, so if you enjoyed the video, again, just give it a thumbs up, and if you think it will be useful, if you found it useful and you think it can be of use to somebody else, share it on your social channels so other people can have it as a reference. And again, if you want to have notifications when more content is uploaded to the channel, subscribe and stay tuned for more content. I'll be more than happy to help you. Have a good one. Bye for now.